Dear colleagues, dear friends, welcome to this international symposium on the representation of language in brains and machines. Welcome to the Collège de France in Paris, and welcome to those of you, I think, who are more numerous, who are following us on the internet throughout the world. We are going to talk today about a very exciting and very old problem, the problem of language. One of the most exciting issues in biology and evolution today. Why are we the only species with language? How does it work? How did it evolve? Can we understand it deeply enough that we might ultimately mimic it in machines? René Descartes, French guy, was already focused on this problem in the 17th century. We remember Descartes for his dualistic philosophy, but if you look at his writings, they indicate that he was really trying hard to be a resolute mechanist, at least for the body. And he considered the body and the brain, at least the brain of animals, as a wonderful machine, just a machine. And he described in his own words how it could work for perception, for action, how the spirits put pressure in the nerves and in the brain. It's little known, but even attention and consciousness were considered by Descartes to be within the grasp of machines. So attention was due to the fact that if the gland was leaning in one way, it could not lean in another way, so we could attend to only one thing at a time. And the fluctuations of consciousness were attributed to the pressure of the spirits in the pipes. And so we went to sleep when the pressure was low. So all of this had a material basis, but Descartes considered the problem of language as the insurmountable problem. And he wrote in the Discourse on Method, 1637, one can readily conceive a machine might be made in such a way that it produces words, and even that it produces some words relevant to the corporeal action that effects some change in its organs. For instance, if one touches the machine in a certain place, it will ask what one wishes to say to it. And if one touches it in another place, it will exclaim that one is hurting it, and the like. But one cannot conceive that the machine could arrange words so diversely as to respond to the meaning of all that might be said in its presence, as even the most stupid human beings can do. Okay, so the machines is stupidest to the most stupid human being. Well, that was the time of Descartes. We know we've made a little bit of progress since then, and we are here to discuss some of the most exciting recent progress. In the 19th century, Paul Broca, Carl Wernicke showed us that there are material circuits of the brain. It's not all over the place in the brain, but in some specific circuits. In the 20th century, a big advance was made by Alan Turing, and then later by John von Neumann. The theory of computation showed us that mechanistic composition of symbols was possible and could go very far, very deep in its ability, perhaps becoming a universal computing machine. Noam Chomsky, of course, redefined the basis of descriptive linguistics, which was started way before by giants such as Saussure, and he founded it on a computational basis, a mathematical basis, and showed us what these computations should be like. And then, of course, there was a revolution in connectionism, artificial neural networks, and we could cite David Rumelhart, Jay McClellan, Jeff Hellman for trying to address the problem of language early on in these artificial neural networks. And today, in all of our pockets, we have little machines that produce and recognize speech. I bet they would have delighted René Descartes. They can arrange words diversely, but do they understand? Do they respond to the meaning, like Descartes was asking? Well, we can doubt it. And are these artificial systems analogous to the human brain? Do our neuronal circuits use a completely different principle to those machines? And why are humans the only species that would possess such circuits, if they do? Using brain imaging techniques, I think we will see some examples of that today, we begin to understand which brain areas underlie the language faculty. But how do they operate? How do single neurons encode the structures that linguists tell us should exist in the brain? Or are the linguists completely wrong? Which is a possibility, I suppose. But perhaps linguistics is comparable to Newtonian physics, a first approximation that will ultimately be replaced by the linguistic analog of quantum physics at the neural level. These are some of the questions that we will ask today and tomorrow. So we here three professors at Collège de France. We have assembled our three chairs in order to try to address this difficult problem. Professor Luigi Rizzi from the Chair of General Linguistics, Professor Stéphane Mallat, in data science, and myself in experimental cognitive psychology. We've tried to assemble a group of experts throughout the world, a group of linguists, cognitive and brain scientists, to shed light on these problems, and also, of course, people in machine learning who, in a certain sense, are meeting Descartes' challenge. We will see if it can all fall together and where are the remaining hurdles, remaining problems to be solved. Thank you for listening. Thank you for being here physically at Collège de France. It's wonderful to restart some of these symposia for which the Collège de France is, I think, famous. And now I'll let the chair to Luigi, who will also give his introduction to the meeting.
Okay. Thank you very much, Stan. I'm really glad to see you guys here, either in the room or connected through the web. As this colloquium is about the representation of language, I think I will just give some information about the kind of properties that, according to linguists, linguistic representations should have. The first property is the open-ended character of human language, right? This really is a foundational issue in modern linguistics. And the roots of these ideas are quite old. In fact, already in the 17th century, Galileo Galilei and the Port-Royal grammarians observed that language allows us to express an unlimited number of complex thoughts. And the method is an extremely simple, almost trivial combinatorial method to achieve that result. There are a few dozens of sounds which are combined to form some thousands of words, and then in turn we can combine the words in a rule-governed way, and that's the crucial point, of course, to form an indefinitely large set of sentences expressing our most hidden thoughts, I nostri più reconditi pensieri, in Galileo's beautiful words. More or less at the same time as Galileo's dialogue, René Descartes, who is very popular today, was already quoted a couple of times by Stan, observed that the capacity to combine words to express new thoughts appropriate to the situation distinguishes humans from other animals. So no other animal, no matter how intelligent it is able to do that sort of thing. And from automata. Of course, Descartes had in mind the wonderful automata of the 17th century. Now, once the concept of recursion was clarified and elucidated in the first part of the 20th century, it was natural to try to abstractly capture the open-ended character of human language through recursive rule systems. And that was the first important contribution that Noam Chomsky gave. Then there's been long discussions in linguistics about the exact nature of recursive systems, and the conclusion at which some linguists arrived in the last 20 years or so within the minimalist program is that the fundamental recursive mechanism is about the simplest rule, the simplest combinatorial rule you can think of. This rule called merge, which says take two elements, for instance, two words in the lexicon, put them together, form another unit, and then you can go back to the lexicon, take another element, and merge it with what you have created, and so on and so forth, recursively. So just that, fundamentally. Now, to the best of our knowledge, all human languages have recursive merge, right? We don't have any human language that says, take individual words and these are sentences, or that just puts together two words and then the process stops, or that limits the length of a sentence to 7 words or 10 words and so on and so forth. No language works like that. On the other hand, and here Descartes' observation continues to be empirically correct, non-human primates possess communication systems with only extremely rudimentary combinatorial processes. They can at most put together maybe 2 signs, but fundamentally that's it. So this raises a number of important questions for this conference. How are recursive procedures implemented in the human brain? very fundamental question. And how is your brain distinct from animal brains, from non-human primates' brains, which seem to be unable to deal with similar properties? And as for artificial systems, are they able to figure out recursive procedures of the kind that children are good at figuring out in typical language development? These are some questions that I'm sure will be addressed directly or indirectly. Now, the second point is the hierarchical organization of structures. So if we think of a sentence, we immediately see a sequence of elements, a sequence of graphemes or phonemes, a sequence of words, like beads in a string, right? But in fact, the real organization of the sentence is different. So this superficial linear organization conceals, in fact, a much more important hierarchical organization, which determines all the crucial properties of the interpretation of the form of the sentence. So take a little sentence like one, the man that met the girl knows the truth. We immediately understand that the man knows the truth, not the girl, in spite of the fact that the girl is linearly closer, in fact, adjacent to the verb. And then the man agrees with the verb, as the second sentence shows, not the girl. This is immediately captured by a hierarchical representation, like the tree given in number 3, in which you see how things work. Fundamentally, it's always a matter of locality. But locality is systematically calculated on hierarchical structures, not on linear structures, so that you can see here that the man is in fact closer hierarchically to the verb, whereas the girl is too deeply embedded to be visible, so that it doesn't do anything. It doesn't participate in interpretive properties or formal properties of the verb. Okay, and then it has been observed by Richard Kane, among others, that the organization is fundamentally binary, or if he is right, strictly binary. That is to say, even in cases in which a non-binary structure would be conceivable, like the double object construction in English. John gave the student a book. We do not have a tripartite structure. Again, we have a fundamentally binary structure in which the first object is asymmetrically higher in the tree than the second object, as can be shown by all sorts of kinds of evidence. In fact, if merge is a binary operation, we do expect binary configurations of this sort. Now, linguists worked a lot on representations of this kind, discovered invariant properties, there are properties that are systematically the same across languages, discovered parameters of variation, and then the detailed cartography of these three structures across language turned out to be a very broad and important empirical endeavor pursued in so-called cartographic projects. Here you have on the right the detailed tree that Guglielmo Cinque proposed for the closal structure. As you see, it's much more complicated than the little trees that we saw before. We'll not go into the details, these details today, but it's important to know that things are complicated at this level, and that there are these projects that are trying to describe structures precisely. Okay, another salient property of language is movement dependencies. And this is the fact that expressions are often pronounced in positions different from the positions in which they are interpreted. So take a sentence in English like 6. Which book should John read? Here, which book is at the beginning of the clause, but it should be interpreted as a dependent of the verb read, as the patient, let's say, of read. And the two elements, the nominal element and the verb, can be indefinitely far away. So we can have, as in 7, that which book is construed with a verb in an embedded clause. Right? Which book do you think John should read? Is a perfectly possible sentence, and they can be even further apart in other structures. So the way in which this property is dealt with is by assuming an abstract representation in which the nominal element is, in fact, in the canonical object position of the appropriate verb, as in 8a, and then which book moves, possibly stepwise in the way indicated by the arrows here, to its final destination, to its final position. And then we get sentences like 8b. Now, movement is characterized by a cluster of properties. One of them is locality. So this movement cannot take place across certain configurations. For instance, we have seen that extraction from a declarative is possible, but if we take as a baseline an embedded question, as in 9a, John wonders who wrote this book, for instance, and we try to form a question like 9b, the result we obtain, which book does John wonder who wrote, is strange, is deviant. That's not a normal sentence. This is a locality effect having to do with intervention, with the fact that who intervenes between which book and the original position from which it is moved. There are various kinds of locality principles of this sort that rule the formal possibilities that are exploited by natural languages. Another property of movement is reconstruction. That is to say, when a phrase is moved, with respect to certain processes, it's as if it had not been moved. That is to say, the interpretation of the element is done on the basis of the position from which movement took place. Take a sentence of this sort in English. Which picture of himself do you think John should choose? This is a perfectly fine sentence, and the reflexive element himself is interpreted as being bound by John, of course, right? The structure means which picture of John do you think John should choose? But himself is not in the right configuration to be bound by John, because it's in a higher part of the tree, and normally antecedents should be higher in the tree configuration, as can be shown by many examples. So why is it that this kind of structure is okay? A classical analysis is that movement leaves traces. So when we move something, we leave a trace in the original position, and the trace is a complete copy of the phrase that has been moved, so that the representation of 10, something like 11, in fact. Which picture of himself do you think John should choose? Which picture of himself? Little unpronounced copy of the moved element. This entity is not pronounced, but is visible to the mind, hence binding can work properly on this kind of configuration. That's reconstruction, systematic property of movement. So we have a cluster of properties that go with movement. Locality, reconstruction, as we just saw, uniqueness of thematic role, of interpretive role, so that if an element has a certain role, let's say the patient or the agent of a certain verb, it keeps that role when it is moved. And movement does not allow an element to pick up additional roles, as it were. Other kinds of dependencies do not have at all such clusters of properties. Take, for instance, the coreference relation, the relation between a nominal expression like Bill in 13 and the pronoun him. Bill thinks that Mary likes him. It's possible to interpret him as referring to Bill. We have a dependency here, but we don't find any of the properties that are associated to movement. There's no locality. The two elements can be indefinitely far apart. There's no reconstruction. There's no process with respect to which Bill behaves as if it was in the position of him. And there is a uniqueness of thematic role, fundamentally, in movement, but not in coreference. In 13, Bill has its own role, let's say, experiencer of think. Him has its independent role, right? So that movement has a cluster of properties that are not observed in other kinds of dependencies. So some questions. What kind of neural structures support movement? And are the other kinds of dependencies observed in natural languages supported by similar or independent neural structures? And then, are artificial systems able to figure out the partition of properties observed in natural language dependencies? So these are also some questions that will be addressed. Let me conclude these very simple remarks. Collaborative projects are necessary. If we want to understand more about language, I think we should have initiatives like this conference. Linguistics has something to contribute, of course, something hopefully important to contribute. That is to say, modern linguistics has built an important body of knowledge on language structure, identified numerous generalizations, and developed an abstract understanding of the underlying mechanisms. So it's clear that this body of knowledge is available to brain scientists, to psychologists, to computational studies, and it's only natural that these other domains dealing with language would take into account the body of knowledge determined by linguistic studies. On the other hand, I think linguists should expect something from interactions of the sort that we are trying to have today and tomorrow. On the one hand, the study of the neural structures dedicated to language can critically inform and influence the abstract study of linguistic representations and offer new kinds of evidence to select among competing hypotheses. We have all sorts of competing hypotheses. Maybe some are more naturally consistent on what we know on the neural underpinning of the relevant systems. Moreover, the precise implementation of artificial learning systems can offer precious indications on the nature of the computational problems involved in language and of the minimal architecture that learning systems must have in order to master salient aspects of human language. So interdisciplinary discussions of the type that is starting now are of great importance, and I'm really confident that we will all know about language more than we know now at the end of these 2 days. And on this hopeful note, I leave the floor to my colleague, Stéphane Mallat.
So let me also welcome you all to this workshop, in particular also the one who are watching us on the web. I do also think, like Stan and Luigi mentioned, that it is a wonderful opportunity to have these three communities, linguistics, cognitive science, and machine learning meet around this theme, because there's probably not enough exchange and share of ideas from these very different point of views. So myself, I'm not working specifically in linguistics, so I'll be spending these 5 minutes or 10 minutes trying to raise some partly naive questions on these issues of linguistic, natural language understanding, but from the point of view of machine learning. So one has to realize that linguistics really has been the model of artificial intelligence in the 80s and 90s. The notion of symbols, association, trying to build structure from that. That was the basis of expert systems. And then we had this deep learning earthquake or revolution or whatever you may want to call it, which has really changed the landscape in artificial intelligence. Around 2010, people progressively realized that tasks, in particular in computer vision, were solved much better by deep learning network, in particular convolutional network, and that has progressively propagated over multiple fields, speech analysis, prediction in physics. Of course, people had been studying natural language for quite a while, but it's really about 5 years ago that also spectacular results have been obtained around natural language for text generation, translation, dialogue, sentiment analysis. And as these techniques have been developing, of course, a number of people have realized that there were limitations. And this game began to try to understand what could machine do, what could machine not do. And most of these predictions, and at least until now, were wrong. At least all my predictions. Very often we thought, well, the machine will not be able to be as good as the visual system to recognize people, faces, and so on. And it happened that it did happen. In particular, in linguistic, natural language, everybody observed, as in all these tasks, these machines are very specialized. And then more recently, you had these huge systems that appear like the GPT-3 of OpenAI with 170 billion parameters, which seems to be able to do one-shot learning, meaning learn from one example, given that these systems are trained over huge databases, almost every text over internet, but just for doing prediction tasks. And this system seems to be able to do multitask, generation of text, poetry, computer codes, translation, question answering, numerical calculations, although, of course, they are far from being as good as the human natural language system. So the question I'd like to raise is not so much about whether machines will be as good or not as good, but of different sorts. What does this machine learning system tell us about models of natural language? What kind of point of view does it bring? And what is really specific about natural language tasks? So what I'd like to do is just to try to detail a little bit these two questions that are going to be partly answered, I think, by some of the speakers during this day and tomorrow. So first of all, let me take the point of view to answer the question of model of these deep learning structure, or more generally, of machine learning. Now, there is something which is impressive with these machines, is that they are essentially generic. Generic in the sense that the same kind of architectures of deep sequential structures, in particular with convolution in neural network, are able to deal with very different tasks. Computer vision, understanding speech, physics, quantum chemistry, predicting the energy of molecule in quantum chemistry, and natural language, as we are going to see in a number of tasks. So what is the common point of all these problems, which in appearance are very different? First of all, you have an input that I call here X, which is a very high dimension. So in speech, you see it here. It's going to be a waveform with millions of samples. In natural language, you are going to have a text, which is indexed by this sequencing indexed U. Images, you have a two-dimensional structure. Now, what is in common in all these data is not only that it's very high-dimensional, but it's structured. It's structured by this index U, which can be time, sequence, or space for image, or in physics, it's the three-dimensional space. Now, this is fundamental, because that's what is defining the notion of locality that Luigi was mentioning. You have the notion of close pixels, or close atoms, or faraway atoms. You have the notion of translation, convolutions. You have the notion of hierarchy. You can aggregate things at different scale, which all these networks do. So in that sense, all these problems share common structures, and this structure, we see it appearing within these neural networks. So what kind of model, mathematical model, have been developed to try to understand that kind of thing? In machine learning, the way you see the problem is you take this input X, this data, and you build a representation of this data in a Euclidean space. The neural network is just a way to build a representation. So the representation here is phi of x. So it's a new vector that is going to represent the information that you give an input. But the particular thing about this representation is that now you can define the notion of similarity within this space just with a simple Euclidean distance. And you can use linear projection to eliminate some components. So suddenly, you are looking at this problem from a geometrical perspective. Now, in this geometric space, there is no more the notion of rules. Everything is about distances. However, you can put constraints. In particular, for example, if you think of grammar as being a structuring relation between different elements, well, that can be implemented in such a space by the fact that your representation is not going to freely move in your space, but is going to remain within lower dimensional structure, which is here illustrated by this manifold. So if you look at the problem from this embedding perspective, there is no more differentiation between notion of grammar or semantics. You could think of this space as being a large semantic space with grammar being constrained within this space. But this framework is the same kind of framework than the one that you're going to use for vision, that you're going to use for physics. And the mathematics that comes out of this framework are very different from the mathematics we are used to see in linguistics, in logic. In particular, you need to understand the geometry of this space. How do you understand geometry in mathematics? You look at how points move within this space. So you look at notion of operators, at symmetries. When something moves, does the property of the answer change or doesn't change? If you have symmetries, you have groups, you have manifold. These are the geometrical tools that are used in mathematics to analyze that kind of thing. The other thing which is very important to realize is that the picture that I've just been drawing is very wrong. It's very wrong intuitively because we are not in 2 or 3 dimensions. We are in a very high dimensional space with millions of dimensions. And that also completely changed the framework to think of the problem. Think of a sphere in high dimension. A sphere in high dimension, the only way we have in mathematics to describe it is by going through probability. Measure theory. What is a point on the sphere? It's a Gaussian white noise. All the coordinates of these points are almost independent. But you have what is called a concentration phenomena that will make all these points stay around the sphere. This is the same phenomena than the one which is that if you throw a dice, 1 time out of 6, it's going to come on the face 1 or on the face 5 if you throw it 1,000 times. So you have this concentration phenomena which creates structure in this very high dimensional space. So the mathematics of this deep learning, in some sense, are much closer to physics. They are very close to the mathematics used in physics. In particle physics, you look at symmetries, you look at operators, you look at the problem in continuous space. When you go from the level of atoms, which in chemistry sometimes has been thought as with analogy to linguistics, you have atoms with letters, you have the notion of valence. When you move to much larger structure, you go through probability, and that's called statistical physics. Now, the difficulty we are all facing is that this mathematics, we don't really understand it. We don't really understand it in the sense that the mathematics of deep network are much more complicated than the current mathematics we use to analyze particle physics or statistical physics, and essentially the mathematical tools are not there. So let me come back to the question. One question which Luigi raised, and that I will raise in my own words again, is to try to understand the bridge between this mathematical point of view, which is essentially a geometric point of view in high-dimensional space, and the current linguistic models based on grammars, based on morphology, which are extremely rich, and understand what's the bridge between these two. This bridge is also very important for machine learning. As I said, we don't understand really the mathematics of high dimensionality. And linguistics is a beautiful case where there is some strong knowledge on the properties, where there are systems that works. And being able to build this bridge is also a way to understand better the mathematics which are behind. Another question, which is a little bit more precise, is what is the role of memory? This role seems to be important in the sense that we've seen that very large system seems to perform better. So I will conclude with a last question around the specificity of linguistics. We know that natural language are created to transmit information. In that sense, they are very specific. We know that there are neural networks which are very similar, which are able to deal with vision with natural language. We know that deep network architecture seems, from data, to be able to learn grammar. So I will come back to the question raised by Stan. How come animals can't learn grammar? Animals are able to have extremely sophisticated visual system, auditory system, so their brain is sufficiently powerful to do these tasks. And how come you have much more stupid system as neural network which can learn grammar? What does it mean? Is it an issue of limitation of animal brains? Or does that point to a limitation of learning algorithm that wouldn't work based on the same principle? I see Stan saying, yes, that's probably the case. I'm opening the questions. And I'd like to conclude with that and thanking all the speakers for giving light to all these points of view. Thank you very much.